So, good afternoon, everyone. First, on behalf of the Atoms Group, I would like to welcome you all to our 2025 seminar series. We are truly honored to begin this year by hosting Professor Gabriele Sadowski. Professor Gabriele Sadowski is a renowned scientist and professor of thermodynamics at TU Dortmund University. She holds a PhD in physical chemistry from T8LM and is internationally recognized for her research on the thermodynamic properties of complex systems with a special focus on pharmaceutical molecules. She received the prestigious Gottfried Wilhelm Leibniz Prize in 2011 and currently serves on the Scientific Advisory Board of the Journal Molecular Pharmaceutics, as well as the German Science and Humanist Council. Her group has made significant contributions to the development of the thermodynamic model PC-SAFT. So once again, welcome, Professor Sadowski. Thank you so much for accepting our invitation. It's a pleasure to have you here with us. Please feel free to start your presentation.
Yeah, so thank you for giving me the opportunity to tell a little bit what we did on modeling solubility of co-crystals, hydrates, and polymorphs. So I will start with, what is a co-crystal? So actually a co-crystal is a crystal that is formed out of at least two different species. As we mainly work with pharmaceutical ingredients, I call one of the species API, which means active pharmaceutical ingredient, but you can replace it by just a molecule. And the other molecule, this is what we call the co-former. So this is just the other molecule that forms together with this API, the co-crystal. Co-crystals usually are less stable than the crystals of the pure species. That means they have a higher solubility and a faster dissolution rate, and that's particularly the reason why pharmacists are interested in to formulate API as co-crystals, because you would like to dissolve them fast in the body. So usually co-crystals only exist, not usually, but always, they only exist as a solid. And in a liquid, they then fall back to the pure API molecules together with the pure coformer molecules. And this is how they usually are also formed. That means usually people take the API as well as the coformer, dissolve them in a common solvent, and then they crystallize and they hopefully get a co-crystal. So the easiest system we have when producing co-crystals is a three-component system containing of the solvent, the API, and the coformer. So if we look at the phase diagram of the API, which is here on the right, the coformer and the solvent, this is the easiest you can get. We have three solids that can appear in that system, the API crystals, the coformer crystals, and then the co-crystal crystals. Usually co-crystals form in a stoichiometric ratio, so this is just in the middle between the coformer and the API, so obviously this would be a 1-to-1 co-crystal. So what can happen if we are in that system? This is the solvent on top, and what you can see is that we have different areas where we expect to have different crystal structures. We can have pure API crystals. That's the solubility of the API and the solvent. And this line is the solubility of the API in the same solvent, but in the presence of the coformer. And as long as we are here in this triangle, we get pure API crystals. The same on the other side for the coformer. This is the coformer solubility in the solvent. And this triangle then is the region where we get pure coformer crystals, which is nice to know, but usually it's not what we want to have. This triangle is where we get pure co-crystals. One crystal structure consisting of two different molecules. This is what we get here in this triangle. Between the three areas, we have one area where we have coformer crystals and co-crystal crystals. together, so a mixture of three crystal forms. And here we have a mixture of co-crystals and of API crystals. So that means this is where we want to be if we are interested in forming a co-crystal of an API on the coformer. So what people usually do is they say we want to have a one-to-one co-crystal out of these components. So what they do is they take a common solvent and then they dissolve the coformer and the API in a one-to-one ratio in that solvent. And then they evaporate the solvent and then they hope to get co-crystals. And what you see here, if you follow the phase diagram, starting from a one-to-one solution of coformer and API, taking off the solvent, we will not enter the co-crystal region, which would be this one, but what we will get is we will get API crystals. So we would not even notice that co-crystals exist because all what we get when we evaporate the solvent is API crystals. So that means this would not work. Following this phase diagram, to end up here in a co-crystal region, you would have not to start from a one-to-one solution, but you would have to start from a solution that contains more coformer than API. That means to the left, then evaporate the solvent, and then you would end up in a region where you would really crystallize a one-to-one co-crystal. This is not intuitive, so that means we need to know the phase diagram for doing this. Sometimes people say, okay, let's assume I have a co-crystal already from somewhere. So I take the co-crystal, dissolve it in the same solvent. That means I would move up here and then take the solvent away again, but you would see even if you take the co-crystal, dissolve it in solution, and then evaporate the solvent, you would end up with API crystals. So this is also what people sometimes are surprised. They take a co-crystal, they bring it into solution, they take the solvent back again, but they do not get the co-crystal back, but what they get is an API crystal in solution with a solvent that then contains all the coformer dissolved. So that is very, let's say, counterintuitive. So that means really we need to know what the phase diagram is to understand where to start to get this or that crystal structure. And this is how we started. We wanted to construct such a phase diagram. So what we do is we first look at the solubility lines of the pure API and of the pure coformer, because this is very clear how this works. We have this kind of solubility equation, which is a simplified form of what we are usually using. But this is nothing else than textbook thermodynamics. So what we need is we need the solid state properties of the API or the coformer, depending on which of these lines we are interested in. So we need the melting temperature and the melting enthalpy. And then what we need on additionally is the activity coefficient of either the API or the coformer in that ternary mixture. And this is what you can take from any model that's suitable. The model we are using is PCSAF. So this gives us the activity coefficient. And then we can apply the same equation once to the API. This gives us this blue line here, or to the coformer, then we get this blue line. However, we cannot apply the same equation to get the co-crystal solubility. And the reason is that we have the melting properties here, and melting properties mean this is the enthalpy difference of the same molecule once in a liquid and once as a crystal. But as we can see here, the co-crystal does not exist in a liquid. It only exists in a solid state. So there is no liquid co-crystal. And that means also there is no melting temperature and also no melting enthalpy of a co-crystal. And that means we cannot apply this equation to get the solubility of the co-crystal. For that, we have a different approach. And the approach is that to get the green line here, we consider this as similar to an erection equilibrium. So we have a solid co-crystal on the one hand side, and on the other side, we have the API in solution and the coformer in solution. And these are the stoichiometric coefficients of the two components in the co-crystal, which is in this particular case a 1-to-1. So this brings us to this equation, which is also known. It's used, for example, for salt solubilities. And we can apply the same equation for co-crystals that says the activity of one component, which is the API, to the power of its stoichiometric coefficient times the activity of the other component, meaning the coformer, to the power of its stoichiometric coefficients is a constant, and that's the solubility product. And the nice thing is the solubility product only depends on temperature. It does not depend on the solvent. So this is very nice. Once we know that, we have this number, and then we can go to any other solvent. So how do we get that? For this, we need to know one solubility data point, because this actually is the composition. These are the mole fractions of API and coformer, which are the same for 1-to-1 co-crystal in solution. So that's the solubility. So what we do is we take one solubility point of the co-crystal in any solvent, then calculate the activity coefficients here using PCSAFT, and this gives us the solubility product. Once we have that, we can then turn the equation around and can say, using this solubility product, we can then go to any other solvent, because this is just a number here, it's a constant, doesn't change. And then we can again use PCSAFT to get the activity coefficients and predict what the solubility is. And this is what we did for several examples. I've shown you on our next slide. This is a co-crystal of carbamazepine and nicotinamide. So these are the two components forming the co-crystal. And this is at a given temperature in ethanol. And what you see is here we have the green line is the solubility of carbamazepine in ethanol in the presence of nicotinamide. The orange line is the same thing for nicotinamide, meaning the solubility of nicotinamide in ethanol in the presence of carbamazepine. And the gray line, this is the solubility of the co-crystal. And the gray area is the area where we do get co-crystals. So this is, you see let's say a zoom in the phase diagram. So that's a 1-to-1 co-crystal. It looks in principle like the previous diagram, but we have a zoom in so that we can see something. So the range of mole fractions is from 1 to 0.8, as you can see. So in principle, it looks as before. So that's the gray area is the area to be once we are interested in getting carbamazepine nicotinamide co-crystals. And the black dots are experimental data, which we took from literature. And this were the data which we used to determine the solubility product. And so that is the correlation, what you see right now. That this is what we use to determine the solubility product. And once we have that, we can then go and exchange the solvent, for example, by acetyl acetate. So the two components are the same, carbamazepine, nicotinamide. And now, but the solvent is a different one. And of course, we get a different picture because the activity coefficients are different. And thus also the solubilities are different. And that's what we got. So that is a pure prediction on the right-hand side. And we had also experimental data for that system. And this is what you see up here. That means you can very nicely see that the prediction was quite right. And that means it's an approach that's very nice to follow. Getting one solubility data point in any solvent, we can predict what happens in other solvents or even solvent mixtures by applying this very simple solubility product concept. Sometimes molecules are also able to form different co-crystals. That means co-crystals in different stoichiometries. This is an example I have here. This is two molecules, TSA and TPPO, and they do form two different co-crystals, meaning different stoichiometries. So the components are the same, But here you see that's the 1-to-1 co-crystals, so the stoichiometric coefficients are 1 and 1. And they also do form a 3-to-2 co-crystal. And that means, of course, we have different solubility products for these two different co-crystals. This is how the picture looks like. The experimental data were again taken from literature, and that's the solubility of the co-crystals, let's say the blue and the red. 1-to-1 is the blue one, and 3-to-2 is the red one in acetonitrile. And you see the two regions, depending on where we start or where we go to with our solution, we get one or the other co-crystal. In turn, once we have solubility data, we can, when we know what the solubility product is, even determine what the stoichiometry is. So that means we measure concentrations, we know the different solubility products, and then we can determine which solubility product, so to say, fits best to the measured solubility data, and this would in turn give us even the information about the stoichiometry. Usually we don't do this because there's analytics for that. We can use PXID, what we also use in our lab, but in principle, this modeling could even be used to determine what the stoichiometry of a co-crystal, of a measured co-crystal, so to say, is. Once we knew that, we then again went to other solvents and predicted these two areas for different solvents. You see dichloromethane, toluene, and ethyl acetate. And for each of these three solvents, these two components form again the two different co-crystals. And what you see is just from looking at it, the areas are different. They are different, particularly in size. And from engineering point of view, if the interest would be to get either this or that co-crystal, you can then take the different phase diagrams for the different solvents and decide which solvent would be the best one really to produce these co-crystals. And of course, the larger the area is, the easier, so to say, is for a process to be there, so the more robust a process is. And if we would have to suggest a solvent to produce one or the other co-crystal out of these two components, we would certainly prefer dichloromethane over toluene, which is certainly very hard technically to reach, to be exactly in the red or in the blue area. So this is mainly what our contribution is. So we say, if you tell us, or pharmacists tell us that's what the components are, they would like to form co-crystals and they would like to produce these co-crystals. The very important question is which solvent to choose. And this can easily be done as a screening once we know what the solubility products are and once we know how to predict or how to calculate the activity coefficients. And we can make a screening of different solvents and suggest the best solvent in terms of thermodynamics to choose for such a process. A particular form of a co-crystal is a hydrate or a solvate. So usually the term co-crystal is used if the two components that form the co-crystal are solids in the pure state at ambient conditions. A hydrate or a solvate is, from thermodynamic point of view, very similar to a co-crystal. So we have two different components and they do form a common crystal lattice. The only difference is that one of the components is a solid at ambient conditions, the API, for example, and the other component is the liquid, meaning the water or the solvent. Thermodynamically, it's just the same. I have two components, they form a different crystal lattice, and that means the approach how to deal and how to model those systems is identical to the one of the co-crystals. but so we do need only two components. That's, let's say, quite a bit easier even. So this is a phase diagram where we have an API, so it's a solid component. And we ask ourselves, what's the solubility of this API in the solvent, which is water in that case. And then we get a very normal eutectic diagram, which all of you know. It ends up here in the melting temperature of the API on that side and in the melting temperature of water on the other. And so we get, let's say, the normal phase diagrams we know from thermodynamics course. So that means we have the API crystal, and if we bring the API in water, we end up with an API solution. What happens now if we have a hydrate formation? A hydrate is, as I said, some kind of co-crystal between the API molecules and the solvent, which is called solvate in case of organic solvents and hydrate in case of the solvent is water. So then the picture looks like this. We have a third solid as before, which is now the hydrate, and it's usually also stoichiometry formed. I have here the case of a 1-to-1 case, can be any other stoichiometry. So we have now two solids again. We have on the right-hand side the API crystals, on the very left-hand side the water crystals, and right in the middle we have the API hydrate crystals. And then we have, depending on the temperature, depending on where we are, different regions. We have, let's say, above this temperature, we have the picture as before. We have only the API solid, which is in equilibrium with the API aqueous solution. Below that temperature, we have the solution in equilibrium, not with the hydrate, but with the API, not with the API, but with the API hydrate. And right of this, we have an equilibrium between the API hydrate, which is here in the API. So again, a mixture of two different crystal forms. And below the eutectic point, we have a mixture of water crystals, meaning ice, and the API hydrate. So that means we have now here again our usually solubility equation where we use the melting point of the API and the melting enthalpy. And below that, we have that we cannot apply this because the hydrate it's again the co-crystal which has no melting point. So that means we have again the same equation as before, the solubility product, which usually is called hydrate formation constant, but it's actually the same as before. It's a solubility product of the hydrate. And as before, we have the activity of one component, which is the API, and the activity of the other component, which is water, and this is the stoichiometry. So this is exactly the same approach as before, and you need, again, a model that gives you the activity coefficient, for example, PC-SAFT or any other model. You need this constant, the solubility product or hydrate constant, as you would like to name it, and then you can calculate what the concentration in equilibrium is, which gives you actually the blue line here. On top of this, for pharmaceutical molecules, you very often do find more than one crystal structure in a solid. So APIs are complex organic molecules, and they are able to form more than one crystal structure, and the different structure of one and the same molecule is called polymorphs. So they can have several polymorphs, not just two, but I have in mind only the case that I can have a second polymorph. The second polymorph has a different solid state properties, so it has a different melting point. So that means now if the melting point of the second polymorph is higher than the one of the first one, as in this example, I have here again another transition point, and I have now a region where I do get polymorph 2, the different crystal structure. Below that, I have the region where I do get polymorph 1, and below that, I get the hydrate of polymorph 1. So this is now happens depending on what temperature you are. You get from one and the same aqueous solution of one and the same API, 3 different solid states. But the solid states only exist in a solid state. Once you have dissolved the molecules, you end up always with the same solution. So that means the liquid looks always the same. You can say the molecules in a liquid, they interact with each other and they do not know from which solid states they originally come from. This is a very nice thing because this means that for thermodynamic modeling, which is concerned only with describing the liquid phase, because the activity coefficients are obviously properties of that component in a liquid phase, you can use one and the same model to describe all polymorphs, hydrates or solvates, or even co-crystals of one molecule. And that's very nice. So the model parameters are not specific for polymorphs, they are specific for the molecule in a liquid. And this doesn't care about actually what the solid is. And that makes it very easy to us to describe those systems. So once we have the model parameters for an API in water, for example, that means pure component and binary parameters, we can calculate this diagram because we only have to exchange the melting properties from going from the dark green line to the light green line. And we have to know what the stoichiometry is and the solubility product for calculating the blue line, but the activity coefficient model is always the same, and also its parameters are always the same. So that's very convenient, and that also helps us to, let's say, find out whether different experimental data are consistent. Because if you have literature data, for example, solubility of polymorph 1 and solubility of polymorph 2, it should be possible to model them using the same liquid model just by exchanging the corresponding melting properties. And that's what we did for quite some systems. And I will come back to that in a minute. I just want to mention again, this is the solubility product for the hydrate or the hydrate constant. And as we are talking about hydrate, and one component is water, we have the activity of that component of water here. And if the solution of our component is in contact with a vapor phase, then this equals relative humidity. This is just a thermodynamic equilibrium condition for water being part of the air and being part of the liquid. So that means relative humidity is equal the activity of water in a liquid, and that means if we have a solution of an organic molecule, which is carbamazepine. In that case, I will show you a picture in a second. Here it is. That means if we bring this solution of carbamazepine, which is another pharmaceutical, in water, in contact with air, and this is usually what we do in a lab, then by this air has a certain relative humidity, this point is fixed. And that means if we have relative humidity here on the y-axis, and we keep in mind that this constant does only depend on temperature. So if we fix temperature, then K is fixed. And if we also fix RH, and that's actually the surrounding of our solution, then this is also fixed. That means we have just one point, one value of X-carbamazepine that gives us the hydrate. Or the other way around, if we have a certain concentration of carbamazepine in an aqueous solution, then there is a certain particular critical relative humidity above which we will always get hydrates and below which we will never get hydrates. And this is what you see here on the right-hand side diagram. This is data from literature, measured data, So this is carbamazepine, and they measured the relative humidity for a given temperature above which they always got the dehydrate. So that's why we have a 2 here, and here it's 1. So this forms hydrates in a 2-to-1 ratio. And below that, there was never found a hydrate, so that's an anhydrate. We can model this line. What you need is the activity coefficient of carbamazepine. We do not need the activity coefficient of water in that particular case because we fix RH, which is actually already the activity of water here. So that we need this gamma here. And PC-SAFT very nice correlates this gamma. So we are now able to say for that particular system, if we have a fixed temperature above RH, let's say we have 25 degrees centigrade, then the critical RH of carbamazepine is about 62. So at relative humidity is higher than that. Carbamazepine will always form high dehydrates, and below that value, it will never form anhydrates. In aqueous solution, that's equilibrium with humid air. And this depends only on the kind of solute, carbamazepine, in this case, temperature and RH. This does not depend on the composition of the liquid because we fixed the water activity. And this has several consequences I want to show you. For example, we have this carbamazepine, which is a pharmaceutical, in PVP. This is a material for making a tablet. So that means we have a tablet made out of PVP and carbamazepine, and we want to avoid crystallization at all. So we would like to be here. What you see is that is the solubility of carbamazepine in PVP. So tablets containing less than 20% carbamazepine will never crystallize. And those who have a drug load that's higher than that will crystallize. If we bring this tablet at relative humidity, that means we at our table at home, we will have a certain temperature and relative humidity. Temperature is 25. And certainly in your room, the RH will not be 0, but let's say it's something between 60 and 70. Then you see the system will absorb water, and that will lead to a decreased solubility of carbamazepine in the polymer. And if we reach this critical RH of 62, which does only depend on carbamazepine, does not depend on PVP, we will get not just carbamazepine crystals, but we will get carbamazepine dehydrate crystals, which have an even lower solubility. And this value is the same as for the pure system. So that means this transition from anhydrate crystals to dihydrate crystals of carbamazepine could have been or was determined just for the pure carbamazepine. It is then valid for any other system as long as RH is fixed. So hydrate formation, that is what the message is controlled by RH only and cannot be influenced by adding something to the liquid because it's just the water activity and that's what fixed. And this is, again, the same system. This is carbamazepine and PVP, and this shows experimental data. And I will not go through this, but the experimental data verify the calculations. And even if you change the PVP polymer to a less hydrophilic HPMCAS polymer, which is always also used for tablets for pharmaceutical purposes, it absorbs much less water than PVP. And that's why the solubility decrease is less pronounced as in this system. That's nice, but and of course, the transition from anhydrate crystals to dehydrate crystals does not change. So that means whatever you add, you will not be able to influence this transition because this only depends on carbamazepine, on temperature, and on RH. Whatever you add to the system, you cannot, let's say, avoid the formation of hydrates or, in this case, dehydrates. And now we can bring this together to make it even more complicated. We can now say we have co-crystal formation and hydrate formation at one and the same time. And the last two slides are only to show you how complicated phase diagrams can really look like. So that's the system you already have seen at the beginning. Here we have an API, here we have a co-former, a one-to-one co-crystal, and the solvent, and the solvent is water in that case. But besides this, the diagram looks as before. And remember, this is where we want to be. We want to form co-crystals. So what happens if the API does form hydrates in water? Then we have this diagram for the API. Also, you have already seen this. And now it depends on the temperature, what happens. So if we have a temperature for the right diagram, which is above the hydrate formation temperature, then so we are above that temperature. That means we do have only API in equilibrium with the solution, and that's what we have. We have the API in equilibrium with the solution, and besides this, we have water. So this is actually the point where we are. So what happens if we now decrease temperature? We decrease temperature, and then we enter the region where we do form hydrates. That means on the right-hand side, the diagram has to change because we now have the solution, which is this point. Then we have the area concentration range where we have the hydrate. This is here. So here's the one-to-one API water hydrate. And then, of course, we have the API, which we have here. So that's on the right-hand side. What happens if the co-former also can form hydrates? Then we have a very similar diagram for the co-former. That means on the left-hand side of this diagram. So we have now also a different picture on the right-hand side. We have, again, the solution, which is up here. Then we meet solubility of the hydrate, which we have here. And then we have the transition point between the hydrate region and the hydrate plus co-former region, which we have here. And then we have on the very right-hand side, which is this point, only the co-former. So this is how it looks like if both the API and the hydrate and the co-former, sorry, are able to form hydrates. And now what happens if also the co-crystal forms hydrates? Of course, you can have co-crystals not only out of two components, but also out of three. And then it looks like this. So we have the co-crystals here. We have the co-crystal hydrate here. And then we have another new area where we have both co-crystals and co-crystal hydrate crystals, besides all the others. So and this is now how the full picture looks like. And that means if you have a system like this, you have to be very careful if you would like to get into a particular region. And this, everything depends on the ratio of the co-former and the API in a common solvent. So depending on where you are, if you have much more API than co-former, then you end up here. You may have a one-to-one, or a little bit more co-former than one-to-one, then you end up here. If you have even more co-former in a solution, you end up here, and finally you may end up here, so you get the co-former hydrates, and certainly depending on where you want to be, you have exactly to know where you start. You see that up here, the difference seemed to be very small in the co-former to API composition in the common solvent water. But as you can see, it really makes a difference from where your starting point is, where you end up. And of course, again, to end up here in this area, you have to be very well informed how the phase diagram looks like. And the 4 lines we can model as thermodynamicists are the ones where the solution is in equilibrium with one of the solvents, of one of the crystals. So this is 1, 2, 3, 4 solubility lines, which we need to know to at least construct the interesting area, which is the upper part of this diagram for somebody who wants to end up at a particular crystal. And we did this. This is the example which I have for that. This is a system theophylline and citric acid. So these are the two components. Both of them form hydrates, and the theophylline on top of this also forms 1, 2, 3, so different polymorphs and hydrates, and this is how the two-phase diagrams look like. And also the co-crystal of theophylline and citric acid is able to form a hydrate. And Linda Lange, who was the PhD student who did that work, she modeled this system, and I will not show you the full diagram. You have an impression how it looked like on the previous slide, just to tell you these are the lines 1, 2, 3, 4, and verified by experimental data. So this is the area where we got pure co-crystals. So that means this is the area to be if the aim is to get pure co-crystals. And this is the area she modeled that would lead to co-crystal hydrate formation. And here to the right, we have the area where we would get two pure theophylline crystals, and to the very left, this would be the area to form pure citric acid crystals, which is obviously much easier to get just from this very complicated system. And the experimental data, this is what we found from literature, agree very well with this prediction, and that tells you once really looking at the system and modeling that system, it's possible to say where to go depending on what the crystal is you are interested in. And with this, I would like to summarize. I have a few very easy take-home messages. So, of course, everybody knows that solubilities depends on parameters, on system properties. It depends, of course, on a kind of solute. I mean, that makes sense. It depends on a solvent or solvents. Of course, you can do everything I showed you also with the solvent mixtures, and on temperature. I mean, this is the obvious part. So that sounds trivial because this is what everybody knows. Particularly interesting is, and this is what I was talking about, is the kind of solute. And this is very often underestimated. Solute can be a crystalline solid. This is what I was talking about. Can also be an amorphous solid, which I was not talking about, but it's a totally different area, but it's as important as this one. Crystalline solids can be different polymorphs, which we have to account for, can be salts, which I did not talk about, but which is also obvious that they have a different solubility, can be co-crystals, can be, as a particular case of co-crystals, solvates or hydrates. That means you have quite a lot of different solid forms that you could have. And that's why if we make a solubility measurement, we do not only investigate what the composition of the liquid is, because I told you that the liquid does not know about this. So the liquid is just a concentration. And for a real solubility measurement, we always need to know also what the solid is. So what we always do is we make a PXAD or a DST measurement to identify what the solid is. So that means we have now to say that this, of course, is also something that is important to know if we are talking about solubility. And at least when talking about solvents and hydrates, relative humidity comes into play. It's not just that we have to know what the solvent and the temperature is, but we have to know what relative humidity is, even if we, for example, measure the solubility in organic solvents. If we do this in a lab and your vessel, your measurement cell has access to relative humidity in a room, there is also water present. The water activity in a system is fixed, as I said, and then you cannot be sure that you don't get, for example, hydrates, even though you measure the solubility in an organic solvent. As soon as you have a relative humidity there and your solid wants to form hydrates, it will. So that means this certainly does not sound trivial at all. And this also tells us that if somebody wants to crystallize something, it's not just enough to know what solubility is. This is just a number. But we really, at least for pharmaceutical, or let's say for a bit more complex molecules, we really need to understand the phase behavior to be not surprised what the crystals are that came out of a crystallization process. And with that, I would like to thank our sponsors, and I would particularly like to thank Linda Lange and Heiner Veit, who did all the experiments and calculations I was happy to show you. And of course, I thank you very much for your attention.